Hello, ladies and gentlemen, welcome back. We will be again talking about AI, and now from the perspective of automotive. And we have got Jiří David from ŠKODA AUTO University, and he will be speaking about using AI in automotive industry. I think it will be very important. Yeah, it is a very exciting field because we collect so many data in the car, and the data can be used everywhere. And then the discussion is how we actually use the data, of course. Hello, good morning. Well, I will be focusing on the possibilities of use of AI, how we can use it in automotive. Well, the automotive industry is an industry where we can use AI for the manufacturing stage, but also in the car, in it, when we use it. I will be focusing on the car, on the vehicle itself, and we'll be speaking about the trend. The current trend, as we might know, is that every new vehicle has got some automation, some degree in automation, and we see the trend of autonomous driving. We can actually speak about the two trends, which is the first trend is the automated highway, and that means the car will go somewhere and the driver will only put in the system the destination, and the whole system will actually start working as an automated system. And another actually possibility is to use the assistance systems that has to do with the drivetrain, with the safety issues, and here the systems, the assistance systems, actually support safety behavior of the driver. They should be supporting his decision making. The first system, called automated highway, is a concept. We have got not technical issues, but legislative issues. That means that we speak about liability, criminal liability. Who should be liable if there is an accident? In the other field, assistance systems, the liability is borne by the driver. That means assistance systems may be implemented instantly, and we get new development with each generation. Those two concepts can be well interconnected technically, and of course they are developed and they actually influence each other. Let me actually speak about the adaptive cruise control, ACC. This is a system which has got various alternatives. We have the so-called conventional cruise control, which works on the road as a simple speed controller and keeps the car at a constant speed. Adaptive cruise control is more advanced. There are actually sensors and radars and cameras used and actually mounted around the car, on the car, which actually gives us information about the moving of the vehicle, about the situation around the vehicle. and we are able to react, or the systems are able to react if there is an obstacle.
And if we are in a column, the cruise control will help us to get closer to the vehicle ahead and still preserves the preset speed of the car in front of us, or if there is a fixed obstacle, it's able to stop the vehicle altogether. Another type of cruise control is so-called predictive cruise control, PCC, which is probably the latest model, the most developed one. There are several modifications as compared to adaptive CC. It can work with information around the vehicle, and it's able to work as well with the surrounding as well. I mean, from traffic signs, it can read them and deduce different parameters. Let me focus on this system, and showing two examples, I will try to explain how neuron networks can be used for recognition of traffic signs, and how subsequently it can be used for processing parameters related to driving to route. The basis lays in the task. The task I'm going to present you is rather complex. I chose just a part that consists of recognizing numbers in traffic signs, limiting our speed. As you can see, the text used for recognition can exist in different formats, in different colors, and so the task needs ability to cooperate with recognition of image. First, there must be ability to recognize a traffic sign, whether it does correspond to the needed format. If the answer is yes, we are able to decode the whole chain of other information. If we concentrate on traffic signs limiting speed, due to digital processing of the picture, of the image, we are able to select a chain of figures we want to recognize, and subsequently we select individual symbols that are then recognized. And let me focus on in what way we are able to start with a graphical format and pass to practical information. In order to do that, I will show you usage of neuron networks. Each of the image is here in a certain pixel number, particular level of recognition represents neurons in the final neuron network. Of course, this is not a completely comfortable way, because we can use with just a certain level of resolution. We do not take on board all neurons. We select just those that fall under so-called mask, and the cross points, the individual points of the mask represent individual neurons for us. These neurons can be further processed on the neuron networks, following different types of neuron networks, whether they are recurrent. As a representative, we have here Hopfield neuron network, or we can use networks that look more forward, here represented by multi-layer perceptron neural network with a backpropagation algorithm. They differ in ways of learning, and therefore in terms of recurrent network, learning time is rather short. However, fitting itself represents an interaction process that can be rather lengthy. On the contrary, multi-layer perceptron neural network, the learning is rather longer, but fitting is shorter. And therefore, if we need a quick reaction, we usually opt for those multi-perceptron networks due to good speed of fitting we need. This is an example of training set. It shows that we have to train the neural network for different sources. The example shows that we do not train only on complete patterns, but we introduce into our training set also some de factus articles or items, so that we get as close to reality as possible, and therefore you can see some signs have a lower readability or are incomplete, and this is the way how we teach the neural network to recognize even incomplete or de factus patterns. With a proper software, we can get the different variants of individual topologies, and depending the software used by us, we have different possibilities to teach, to program topology. We can program it by itself, and depending the algorithm of learning we choose, the result is also different. This was our first application. The second application will be oriented on completing the application. We will have a look at how we can use today different systems for predictive cruise control. And we are also discussing the fact that this predictive cruise control can use data obtained from GPS. It can also monitor the condition of the road surface, the condition of our vehicle, and therefore can predict cruise conditions for the following distance, dictating the format of driving, style of driving, so it is eventually safe and pleasant for the crew of the vehicle. So we will have a look at these systems. They are shown on a simplified model. As a starting point, we use mathematical and physical model of the vehicle movement. Some basic equations are set describing all the forces involved and all the parameters influencing the style of driving under given conditions, and we try to complete it with further parameters that we can obtain during the driving. The main parameter we are interested in is adhesion. In other words, how well we are able, how safely we are able to respect adhesion parameter of our tires to the road surface, which has a clear effect on our safe speed and safe braking. Adhesion or grip value is connected with many different things, such as condition of tires, condition of the road surface, speed of the vehicle. We can use basic physical equations for description of the situation. However, when we drive, we do not have a chance to get such data, and so we have proposed a model of censoring the road. The model uses a capability of digital image processing and is able to determine what's the surface of the road, and in addition, based on data of the surface of the road and the vehicle itself, it can get the necessary preconditions for solving the situation. It's a more complex task, and therefore there are more neuron networks involved in solving such a task as compared to the previous example, previous case, where just one neuron network was enough. We propose 3 neuron networks here. The first one predicts interval value of coefficient of adhesion based on 3 categoric variables that characterize type of road service. With camera, we are able to recognize different types, such as concrete, asphalt, gravel, etc. We can also define the surface in terms of its condition, whether it's a new surface or whether it's been repaired in the past, or whether there is ice layer on it. And the third parameter is what's the surface of the road depending on the weather, whether the surface is dry or wet. These are basic variables we get through analysis of the image, and based on the variables I listed, we get the upper and lower limit of the coefficient, which is further used for further calculation. The second neuron network is also predictive one. We deal with prediction of slowing down interval. In other words, we want to find out when we have to start slowing down in order to ensure safety of driving. In here we have, as I said, the second neuron work, which works with the outputs of the first neuron networks, and in addition we have parameters characterizing braking and the slope of the road. We can get either from a given map system or from the GPS system, using all the information it produces. The third neuron network we use for this task gives us the final result, which is prediction of a maximum value of slowing down in the 3 forms: minimum, maximum, and median. And it says to the system when it is to slow down based on either an obstacle present on the road or some other type of limitation. And we have to take into account also type of vehicle, whether it's a small, medium, or bigger car, also condition of brakes, and also a load of the vehicle. All these data are parameters we can obtain quite easily without problems due to different sensors that are involved in solving the task. The resulting value generated by the mentioned neural networks is then passed to steering unit, and this steering unit reacts practically to the situation analyzed. Of course, what can happen is a situation when unpredictably, suddenly, there is an obstacle, such as, for instance, deer crossing or some other animal crossing the road. If so, the information is passed over to other assistance system that will do all needed for a fast breaking down and prevention of collision with the obstacle.
As for the two tasks mentioned, I would say that the first task will be used for classification when we use neural networks for digitalization of the situation, and then we digitalize it, and the output are the data, and the data are used as inputs, and we can process them. I forgot to mention that once we have actually read the numerical symbols, we just put them into a digital piece of information which is processed later on. The second task showed us the possibilities of prediction. In many cases, the neural networks are used by us for predictions of values which we need, which we cannot actually derive from mathematical background, and it is rather the neural networks that actually cover for the mathematical background. The advantage is that we can actually process any values of any nature, and those values, if processed or used conventionally, we would not be able to actually put them together, but we can do that if they are part of the neural network. Let me sum it up by saying that as technology develops, we attempt to actually replace the human being, the worker, in the processes by a more developed system. And we try to describe the methodology. And those AI models can actually solve various tasks. And what I would like to say is that AI methods have not reached their limits yet. There will be more development in this regard. And that's why we may expect their further proliferation in various fields, such as automotive or in households as well. And the vehicle, as presented by me at the beginning, we have the objective there, and that is autonomous driving. And whether we actually reach that objective soon or later, that will depend on AI largely. Thank you. Oh, thank you for this very nice lecture, which actually showed us the technology background and also engineering and automotive. We see what people or workers always address in those technical fields. Now I'd like to ask you, how often do you read that sign, that tag? And if it says that it has to be damp or wet, then it is written in a local language, right? Well, of course. As for the text, let me explain it. This sign will be segmented into subsegments, and then we look for chains, and they will be analyzed separately, the chains. That means we know what signs we have, and that's why we are also able to do the following. If there is one sign with some text, then we know in advance what text there will be, and that is why we can teach the neural network using that text expected there. Well, as for actually reading it by reader or a camera or a sensor, we have to have a high enough resolution. We have to have tests at various speeds, and the sign will be read several times repeatedly, and then it takes some time so that we can actually create a complete image. Another question on my part, does it happen that those limits which are actually in the rear of truck will also be read as a sign? Not really. The cameras know where the sign is placed, and moreover, we can also focus on the space which we need to be described or read. Okay, let me ask something relating to it. How often do you think about upgrading the models? Well, what models do you mean? Neural networks. And I assume that you will have a respective model in the car so that it works. So how often do you upgrade those models in the cars? Well, I have to admit that we have not been addressing this issue yet, but in my humble opinion, I think that today we can actually update software autonomously. Even in the cell phones it happens autonomously, so it is not an issue. If there is a change in the software, then we can actually update it, upgrade it. And if the car or the driver comes to checkups regularly to the service, to the car dealer, then they can actually upgrade it. Okay, and I would say that in the last century there were the first attempts at reconnecting the cars, interconnecting the cars. And the question is whether that is also possible, that cars actually exchange information. Yes, of course, this is how automated highway works. I mentioned that there will be vehicles or machines that will communicate between each other. Of course, the cars will actually exchange information with each other. Okay. I would like to ask about this situation when cars are interconnected, and how about the driver? If the driver is in the car will the car actually recognize the driving style of the driver? Some driver likes speed. Yeah, there are various studies conducted. There was an international research team, and they used a driver, and the network actually learned the habits of the driver. That would be one alternative, possible alternative. Or I imagine, how should I put it? Safe driving, I would say. A safe driving model for the average driver. Well, I imagine that we will have chatbots driving for us. However, I would like to thank you for this very inspiring presentation, and now we will switch